Okay, great. Lecture 2. I'm not going to assume you guys are all experts in error estimation. I'm not going to repeat that again, but I will use it. Okay. All right. So the second lecture is about block encoding, which is a technique, again, developed back in around 2018 and 2019. It's known as Asian as the tolerization, for example. It's really recent state-of-art techniques. I'm going to go back to the Hamiltonian simulation and just talk a little bit about the motivation for that. Before that, I want to emphasize this part of my, when I talk about QSVT, which is going to be a way of implementing block encoding. QSVT will only work for time-independent problems, which is going to be the second part of my talk, the lecture 2. But the first part still works equally well for time-dependent. So we have match polarization, and then we have bound where we know, okay, alpha H is actually a quantitative scaling. Several algorithms. You may wonder, oh, why am I care about post-error algorithm? My choice is already easy to implement. A nice bound. It's pretty cool. So it really depends on your purposes. You may not have to use other algorithm. I have a lower bound from no fast forwarding system, which says linear in T. I want to get the lower bound. If you look at Trotter, you got T plus some 1 plus P over T, which is a power. It's not an exact linear in T. And in terms of error, you have a polynomial dependence on error, which is already pretty amazing, but it's not low dependence on the error. So the motivation for many of these post-Trotter algorithms is that can we reduce the cost further to make it error even, the cost even. So now comes the truncated Taylor series, which is our best friend of truncated Taylor series. And the H, suppose this H can be written as a linear sum of a number of terms, where you can expand these parentheses and put each of the terms down here. So the motivation from here is that if you look at these algorithms, post-Trotters, you will find that these algorithms can get away with linear dependence in T, which matches the theoretical lower bound. Whether that's hardware more friendly or not, questionable for experimentalists. But this is at least something that is pretty cool theoretically. Another question is, can you even get better? Instead of multiplication about the error and the time, can you even get an additive error bounds, which is even smaller? Instead of multiply lambda, you just add them, which is smaller. The analysis is similar. You do the same analysis as what I told before, which is general, regardless of what kind of algorithm you have in mind. But here I'm going to talk a little bit of how do you implement this at some quantum circuits. As again, why you need something new, something at least conceptually new for the quantum circuits. Again, I said if each of the H are unit spaces, the strings of many-body polys, each of them are unit. You have two unitary, you multiply them together, it's still a unitary. What about a linear combination of them? Now, think about an example. You do not have to answer, but everyone take a few seconds. Try to think about the example. You have two unitary, you do a linear combination. That thing is no longer unitary. 2 seconds. Okay, some examples. If you have unitary U, you minus itself. Minus unitary is still unitary, right? You get 0. Okay, done. What about other things? Well, you can think about x plus y, where both of them are unitary. Well, the point is that the normalization doesn't work well. The norm is no longer 1. All right. Now the question is, circuits are unitary operations. How do we implement non-unitary matrices or non-unitary operations? Or how do we think about it conceptually? Okay. So here is the thing about block encoding. The idea is that if A is not unitary, I can embed it. I can do a dilation in certain sense. I can embed it in a larger unitary. And then imply the larger one, then as part of the system, it's basically applying the actual non-unitary matrix that I'm interested in. Does that make sense? So this is the idea of block encoding, which means that I'm going to dilate the system and put a number of ancilas to make the dimension larger. And I'm going to make it a unitary, and A is the interesting non-unitary matrix that we want to implement. Is on the top left corner. This is ideal. Isn't that any problem if I just write it in this way? If you think about this carefully, there's immediately an issue. What is the operator norm of a unitary? 1. Yeah, I heard the answer. What is the operator norm of an arbitrary matrix? Can be arbitrary large. How can you, embed a large thing in an operator one? Do not make sense, right? So immediately, one thing you realize is that you need to divide the normal to make sure it's smaller or equal to 1 so that it can actually embed it in a unitary. So this alpha is actually an upper bound of the operator norm. It can be larger than that, but it cannot be smaller than that. So in block encoding, we call this the sub-normalization factor. The reason it's called the sub instead of normalization factor is because it may not exactly equal to alpha. It's a sub-normalization factor. All right. Now we wonder, what if my algorithm has an error? Please.
If A is unbounded, then can we still do something similar?
That's a wonderful question. The answer is yes, no, and yes. No is that it's unbounded, it's infinity, there's no way. But if you think about the unbounded operator, even classically, we do not directly implement an unbounded operator. We always discretize it because finite dimension is going to be implemented. But in all the post-Trotter algorithm will have operator norm dependence. In which case you need to be very careful about what kind of discretization that you are using in order to make sure the error do not blow up. Very good question. Any other? Okay, I'm going to continue. So you have an algorithm, which means that this A tilde can be our U tilde, which is not the exact unitary operator you want to implement. You pay an error. And the error, again, is bounded by some epsilon. So it can be not A, but A tilde. And you have a number of MRs in a qubits. So here is a nice cartoonish definition of block encoding. Now it's the mathy definition of block encoding. I just show you. It's not too mathy. Let me just explain. So we call this guy L alpha, which is a subnormalization factor. M is how many acyclic qubits you need, which I will discuss later, exactly how many acyclic qubits you expect. And epsilon, which is the procedure of this encoding. So alpha M epsilon block encoding is defined in this way. Particularly when epsilon is 0, you can drop this the third component. You just say alpha M block encoding. And what the heck is this guy? If you think about this carefully, there are multiple ways you can interpret it. I think just for understanding purposes, I'm going to give a number of equivalent understanding as this side. I will give the matrix form, and I will also give the tensor form. I think it's helpful if the first time you see it, you work out a little bit of the algebra and get a better understanding. So this is the first understanding is that although it puts it in this way, but the dimension is not an addition. It's not plus m dimension because we are acting on qubits. It's multiplied by 2 to the m qubits. In other words, if you think about one theta, you are already doubling the space dimension, doubling the dimension. So one theta is pretty good already, which I will show you as a series of everything. Second is that now let's try to check the matrix form. And if you are a tensor person, I will then check the tensor form. Check the matrix form. What this guy means is 1, 0, 0, 0, 0, 0, and you tensor it, you get IN 0, 0, 0, 0, 0, derivative. And you look at this guy, which is just a complex conjugate of it. And now, this UA, you just take this matrix form, you multiply. Imagine you multiply this on the left, you multiply this on the right. What do you get? You pick out exactly A tilde divided by alpha. And now you are multiplying the alpha, so you get A tilde itself. Now, if you think this is a reasonable, shake if you think it's not. Okay, I hope this is somewhat reasonable. Second is what about the tensor population? This for simplicity, I'm going to take the number of zeta qubits to be 1. Then you have this matrix form. What this matrix form in the tensor language is essentially saying that you have a 0, 0 tensored with the first component. So this is 0, 1, and 0, 1. So this is the labeled as 0, 0. This is labeled as 0, 1, 1, 0, 0, 1, 1. Right? So you have 0, 1 tensor with the component, and so on and so forth, tensor with a bunch of things that you don't really care. Now you try to think about, I'm going to put this in the middle, inner product on both sides, sandwich it by some zeros and Scylla qubits on the left and on the right. What do you pick out? You pick out exactly this thing. Not if you're okay with this, kind of, because here is a tensor identity, so there's nothing done on this component. Here I have 0, so when I acting 0 on 0, the overlap is 1. And here, when I act this 0 on the left-hand side, the overlap is again 1. They're all gone. I'm left with A tilde divided by alpha times alpha is A tilde. So this expression is basically saying A minus A tilde is not bad. Kind of okay? Okay. Now, if you have circuit, this is the circuit. You have a blocking coding. This is the system that you have, and this is the Scylla qubits that you have. You just put this as a blocking coding circuit. You measure it, and the outcome gives you this. This is the 30. Again, if you want to say a little bit more in either the matrix form or the tensor form, you can do both of them. I guess I will not do both of them for you. Maybe let's just take a look at maybe this tensor form. Now, the tensor form UA acting on this Scylla qubits and the system qubits, because of the 0, 0, 0, 1, 1, 0, 1, 1 thing, we will get this plus a bunch of other terms in other bases that we don't really care in the first register. And now you imagine, what if you measure the first register, this 0 to the m? You get 0 to the m. After that, with certain probability, after that, the state collapses into precisely this. So this is precisely what this circuit is showing. Please.
1 second. Do you want the box? So is it possible that you would have to run the circuit many times depending on the stars to get that 0 measurement?
Perfect question. Great question. So I do said that it comes with a probability. Now let's think about, if I have alpha blocking coding, what should the probability look like? So now if I have an alpha blocking coding, if you look at the matrix form, you multiply it out, or you look at this form, you get only this part as what we want. So the amplitude of it is going to be blocking coding. In other words, this is actually a very important point, which I will discuss in the end of today, this lecture, is that alpha is crucial. For example, if you have L time step, if your alpha is, say, 1.01, but to L's power, or maybe L2, which is not a very harmful number, but to L's power, then the probability you will get in this post-selection procedure is going to be exponentially small in the number of time steps, which is terrible. This is an exponentially vanishing probability is going to be terrible. That's why in the last technique I'm going to show you is the so-called OAA. This deals with unitary dynamics, which is the focus of today's talk. If you have non-unitary dynamics, say in open quantum system and so on, there are generalization version of it to make sure, naively speaking, if you have a 2 blocking coding factor on the denominator, you can always repeat your circuit 3 times, 3 Curies, and to make it 1 blocking coding factor. So you multiply 1 raising to the L's power. Well, that's still 1. That's actually a very, very important point, which we will show in the end. Very good question. Any other further question? Okay. Yeah, please.
Oh, so if you don't measure 0 to the m, is it always just a useless result, or can you ever get information out of that still?
Oh, that's a good question. So actually, in terms of the circuit implementation in all these, we're not going to perform mid-circuit measurements. That's like quantum error corrections. So the idea would be I want to do the block encoding or do this coherent circuits as long as possible, and postpone this post-selection with the probability at the very end. And in between, I'm going to do some techniques such as boost the success probability to a higher block, to a better block encoding factor, so that in the very end, I guarantee this is of omega-1, which is bounded, well, say 0.5, that probability that you will get the result that you actually want. Yeah, this is a very good question. And in reality, in many cases, we ask about what is the cost if you, well, again, this block encoding is different from trotter. Trotter do not have ancilla. You do not need to do post-select, right? There's no probability issue associated with trotter. However, block encoding, you do need to measure in the end, and you do have a probability. The question is, can you make the probability as close as 1 as possible? So in theory, we totally do the analysis by looking at the probability. We say, what is the probability? What is the cost to make it 1 minus delta? Well, delta is the failure probability that is tiny. Can you make it, say, log dependence on the delta inverse, which is considered to be a good algorithm? Pretty much most of the algorithm can be made in that way. Say, quantum phase estimation and so on and so forth. There are always tricks that one can play to easily make it that way. All right. Any further questions? Okay. Now, I'm going to assume you are okay with my definition, either the matrix form or the tensor form or the circuit form. Pick one of your favorite. One immediate question. I have a definition. Is it well defined? You know, you can write any definition as you like and prove a zillion of beautiful property associated with it. But if it's an empty set, then you're not doing anything good, right? So first of all, whenever you have a definition, first thing, ask yourself, is it well defined? Is it not an empty set? Is it at least something general? The answer is yes. So, trivial example, if the matrix we are considering is unitary already, it itself is a block encoding. It is a 1 and with 0 ancilla qubits and 0 error block encoding of itself. Okay, what if I have a general A? The claim is that alpha 1 block encoding is general. So 1 ancilla qubits, you probably mentioned, this is general. I'm not saying this is efficiently to calculate, to compute, implement, but I'm just saying this the definition itself is general. Okay. How do I show that? Okay. Well, I'm going to assume that A is bounded by 1. You can be, wait, it doesn't make sense. A is upper bounded by alpha. It will not necessarily be upper bounded by 1. Well, then take A divided by alpha as the A that I'm considering. That is upper bounded by 1. Right? Renormalize it. So suppose A is upper bounded by 1. We know that any matrix always have this singular value decomposition, where this sigma is a diagonal matrix with the singular value. Not all matrix is diagonalizable, but all matrix has a singular value decomposition, which is pretty cool. Then what you can get is, it turns out, well, not necessarily, this is some algebra that is not important at all, but just to show you that, turns out if you just do this thing, which is as UA, and this is precisely the block encoding that we can get. So for any matrix of A, there's always a 1 block encoding of it. Is it efficient to be implemented on quantum circuit? Maybe, maybe not, but at least it exists. Are you okay so far? Please.
It sounds like there's the overhead of possible calculus. If you say if A is 5, then you have to do some.
Yeah, that's so here I'm not using this as an algorithm to implement block encoding. So the next question would be, this is just showing on a formal level, at least the block encoding exists. It's a general enough concept. The next question would be, what types of matrices, say what types of Hamiltonians that are simple enough so that I can construct a block encoding of it efficiently. Right, that's the two separate questions. Okay. So now let me answer that question. What type of Hamiltonians are easy to? There are a bunch of them, but for simplicity of today, for example, sparse matrix Hamiltonian is easy to implement, and also capable Hamiltonian is also easy to implement. If you have linear combinations of unitaries, it's easy to implement. I will show you how later. But for here, if you have a matrix representation, this is something. C is 1C. If you're not, say, a computer scientist or mathematician working on this stuff all the time, C is for once and just take away the result. The result is that if you have an S-sparse matrix that is a Hamiltonian, you can always get S-sparse as the subnormalization factor with 3 ancilla qubits efficiently with only this little cost. So if you are dealing with local Hamiltonians, if you are dealing with sparse Hamiltonians, which are cases for many of the physical systems anyways, you are fine. You don't need to worry too much. I'm not going to, these are some references on how precisely to construct the block encoding, but I'm not going to dive into that detail. That's important detail. Okay. So from now on, I'm going to look at H, which is a Hamiltonian that is already block encoded. And now I'm going to, I have the concept. I tell you the concept is not an empty set, it's well-defined. The next thing I'm going to discuss is its properties. Why do I need this concept? Is there any nice property allow me to construct reasonable, helpful algorithms? So there is a question, please. That's just some technicalities depending on the input models that we have. There's no, I think people have been improving this arithmetic circuits ever since. This may not be the most updated results, but the point is that it's doable. Good question.
So that norm H is less than 1, that is
which one? Oh, norm of H. Oh, great question. If norm of H is not 1, then you take H divided, say norm of H is upper bounded by alpha, you take H divided by alpha as a matrix we deal with. So if I have S block encoding of H divided by alpha, which is a norm 1 matrix, that means that I have alpha times S block encoding of H.
I see. So which means that if the norm of the H to be founded, always block.
Exactly. That's extremely important, which actually forbidden the efficient implementation of block encodings on unbounded operators. You need to be careful. I'm not saying it's impossible, but to make it efficient, you need to be more careful compared to spin models. Good question. Any other things before I move on? Please.
Yeah. Do you want the mic? Hello?
Here.
Yeah.
Here.
Can you catch this? Okay.
Expression there includes the success rate of your measurements already?
Oh, that's a great question. So now I'm saying I can create this UA circuit. I'm not doing the post-selection. The post-selection success probability is associated with this subnormalization factor. The reciprocal of it is basically all success probability. Right. Good question. Any other? No, again, if you have a S-sparse matrix, S is going to be a lot smaller term compared to 2 to the n. Right? Any other question before I move on? How am I doing this time? Okay. Properties. I have a definition. So I want to derive some properties of Rocket. So first question is, dated back to that question asked by the audience. So if I have a block encoding of A, or alpha block encoding of A, if I want to get a block encoding of a constant, multiply by that. Can I get it? Yes, you just multiply the denominator and the numerator by the same thing and you get it. It's the same block encoding. Agree with me? Cool. Now, if I have block encoding of A, block encoding of B, can I get a multiplication of it? The answer is yes. And this is precisely the circuit that you can get that. The point is, before I show you why this is the case by checking the definition, the point is the subnormalization factor become multiplied together. The number of ancilla you need is additive. You need to add both of them together. This is kind of important. So you can imagine if you have L time steps, each of them they have a subnormalization factor of 2, you are doomed by this naive implementation because you have 2 to the L by multiplying everything together. That's what I'm going to show you how to avoid it hopefully I have time in the end of this lecture. Okay. The point is there are ways to avoid it. Oh, okay. So there is some calculation. I guess it's not important at all. The point is we just faithfully check the definition. And there are A plus B ancillas. You put all the A's on one side, all the B's on the other side, and you work out some algebra, and you get A2 times B2 times. And you can use any of your favorite block encoding definition. The point is, well, there's some error. So the point is really that the block encoding subnormalization factor multiplying together, and we will use this later. And the ancillas you need is added up. Okay. Third question. I have scalar and I have multiplication. Can I do sum? If I can do sum, I can do linear combination. I can do a lot of things. Can we do sum? This is the simplest version of the so-called LCU, short for linear combination of unit rays, which means that if you have one unit ray, another unit ray, it can be block encoding of something. So the linear combination of unit ray for block encoding is called linear combination of block encodings. But in the end of the day, linear combination of unit rays, well, there are some technical details to be worked out. But the point, let me just show you one example of it. Suppose you have a one block encoding of A. Again, if this is alpha, you just make it A divided by alpha. And you have one block encoding. Can I get the sum? The answer is yes, you do this. Let me see, do you want me, I think it could be helpful if I write it down how to, if I send it to the projector, you can no longer see it. Okay, let me just say it verbally. You start from 0 in the first register. You get a hard mark, then you have uniform superposition. 1 over square root of 2, 0, 1 over square root of 2, 1. Then you control on UA, control on UB. When you control, when that is 0 on UA, you apply UA to the 0. And this apply UB to the 1. In the end, you hard mark back again. Actually, when I try to compute block encoding, I prefer to compute it backwards. So this measure result will give me 0 out. So I go backwards. This is a uniform superposition. So I have a state from here. I have a state from there. Block encoding, the definition is saying we do an inner product. So I will do the inner product of this state, which is uniform superposition, and this state, which is 1 square root of 2 UA acting at your state, plus 1 square root of 2, 1 UB acting on your state. Once you do that inner product, if any of you want to do the calculation quickly right now on paper, you'll see that you get 1/2 UA, plus, because 1 of root of 2, 1 times another 1 over root of 2, right? You get 1/2 UA plus 1/2 UB acting on the state. And the 0, 0 cancelled, the 1, 1 cancelled. Right? So this is precisely a 2 block encoding. Because the denominator is 2, you get A plus B divided by 2. The block encoding becomes a 2 of A plus B. So what is the takeaway of it? It turns out if you have a block encoding, alpha block encoding, and a beta block encoding, you want to do the linear combination of them. The new block encoding, the subnormalization factor will be the added addition of it, which is quite reasonable, right? Let's think about the operator. I mean, what is the norm of what does this alpha mean? The alpha means that the upper bound for your matrix When you have a matrix A plus B, where A is bounded by alpha, B is bounded by beta, their norm together is alpha bounded by alpha plus beta. That's pretty reasonable. Do you agree with me? So here I'm saying one is alpha bounded by 1, the other is alpha bounded by 1 as well. 1 plus 1 give you 2. That's the same as the calculation going out here. Not if you are happy with this. Okay. All right. So what I try to say is that linear combination is not a problem. You just play around with it. Generally, how do you do linear combination of unitaries? I don't think I will write out the circuit definition, the calculation for you. But just to say, general linear combination of unitaries can be done, and general linear combination of block encodings can be done. And here is the circuit for it. And the calculation is exactly the same. You go from forward, backward, and the inner product. If you're interested, come to see me and I will calculate it for you. It's not, it just take me a few minutes, but due to this, I don't have anywhere to write. So you can see this is pretty similar as before. So this select oracle is going to be controlled on how many terms you have. As previously, we are controlling on 0, controlling on 1. It's pretty reasonable. And this prepare and prepare dagger is going to give us the coefficients we want. Previously, we have hardness, which will give us 1 over root of 2. 1 over root of 2 times together, we get 1/2. So that's why we have like root of C divided by the normal bit. This is like 1 over root of 2, which is your prepare dagger. And you work out the math part of it. You will see this exactly implement a C1 block encoding, exactly implement the linear combination of unitary. Where this subnorm normalization factor, guess what? It's the sum of everything, as what we expected. We said alpha plus beta if I have 2 terms. What if I have L term? You just sum everything. It's as expected. Are we okay so far? And the ancilla qubits we need is log of that. For example, sum 2 term, I need 1 ancilla qubits to represent uniform superposition between 0 and 1. If I have L term, I need log L qubits to represent the superposition over that. Okay. So what's the point of all this? The point is, if you don't like the previous properties, just forget about the derivation. But the point is, we have sum, we have product. We can implement any polynomial. And any function can be approximated by polynomial. We can implement it virtually and essentially anything. You agree with me? It's really efficient. Well, that you need to do carefully analysis, but at least you can do it just using the properties. What are the examples? For example, well, Hamiltonian simulation. It's an exponential function of h. If you have a block encoding of h, you just do this. You get Taylor series, which is a polynomial approximation of the unitary, and you implement using the previous rule, you get some. Great. If something, then it's an exponential matrix of h. It's inefficient, well, you need to be careful, but at least you can do it. H inverse quantum linear system algorithms, QLSA. Can you do it? Yes, you can. It's an A inverse. So the techniques that I'm talking about here, I'm only going to apply to Hamiltonian simulation scenario, but this can be applied to all of these problems. You can work it out if you're interested. All right. Now let's go back to Hamiltonian simulation. I want to address a little bit about this totalization. Now, the Taylor expansion. Now I have the Taylor expansion. Again, I said that, okay, because this is a sum of linear combination of unitary, it's no longer unitary. But now you know how to implement linear combination of unitaries, right? So, for example, this is an algorithm. We have a local truncation error. Because this is a Taylor expansion, you can write out the remainder term and get a truncation error. I'm not going to repeat it. Just trust me, this is what it is. And now, recall this is not unitary, so the error is not exactly sum of all the local truncation error. You get an exponential factor, but it does not change our cost estimate, if you recall. We still just need R times L to be of order epsilon, which tells us you have some exponential. Well, it's better to be bounded by some constant, otherwise it's not going to be bounded by some small procedure. And then you have this freedom to choose k, which gives you that k can be in this log manner. This is each of the short time steps, what you do. And this L tells us how many time steps we need in total. So this is how many time steps, L time step, alpha times t. Each of the time steps, you do a LCU with respect to this many k. You first use each of these block encoding of h to construct a polynomial, and then you add up them together. The cost overall is going to be this. As I claimed earlier, it's almost linear in time t, which matches the theoretical lower bound. Amazing. Are we okay? I admit the circuit is much more complicated, which is true. But at least this is something. And then I will show you QSVT, which is a way to simplify the circuit a tiny little bit. Still fairly difficult compared to Trotter, but at least it's something. Okay. Now back to this subnormalization factor issue. You have all these terms, the sum of all the norms, recall, is going to be the new subnormalization factors in LCU. So going back to the previous question, this e to the alpha delta t, for example, if I choose this alpha delta t to be a constant, let's say log 2, then e to the log 2 will give me a factor of 2 at each of the local time steps. You multiply them together, 2 raising to the L power, you are good. Agree with me? But in the very end, I will show you a way. If you have a block encoding factor of 2, you can always repeat the circuit 3 times to make it 1, together with some other operations. But just to say, this already carry all the analysis. There are some little bits we need to be discussed, but we will postpone it to the end of this lecture. Are we okay so far? Pretty amazing. You will be like, well, Tinder series is our good friend. It's already pretty amazing. Why do I still need other techniques? It's actually the lower bound, come on. But if you think about the following question, how many ancilla qubits you need here? When you make a multiplication, you add them together. And when you sum a bunch of them, L terminal of them, you take the log. And you have a polynomial in terms of k. Let me just do a rough calculation. This may not be tight, but you have a huge, number of ancilla qubits. Terrible. Do you agree with me? Great, but the ancilla qubits is terrible. Can we do better? It turns out QSVT or QSP, which is the prototype version of QSVT, is the technique which I'm going to discuss in the next part of the lecture in a naive case. Saying that if you want to implement a polynomial, you get away with one case, forget about the other things. Pretty cool, right? Isn't that pretty cool? All right. So now let me talk about QSVT. What is QSVT? First of all, again, we're going back to this matrix. Any matrix has the singular value decomposition. Please.
Right behind. So before moving on, we have linear number of query complexity.
Yeah.
And for each query, we need to post-select the all zero measurement outcome, right?
That's a great question. We do not.
We don't? Oh.
We do not. So it turns out you can multiply all of them together. What I'm trying to say is each time step for Taylor, we have 2 block encoding factor. In the end, there is a technique to make the block encoding factor 1. And I again use the properties of the product of the block encoding, which multiplies all the terms. And still, so far I have to not do any post-selection, not do any measurement. And it will be 1 raised to the L power, which is still 1. And finally, you do the measurement there.
Then the measurement, the probability of the desired measurement outcome is converting to 1. That's what.
Yeah, exactly. What is the reason for that? Because you have a circuit, it's in Hamiltonian simulation. Although it's not a unitary, but it's approximating a unitary. And you are absolutely away from the actual unitary, which have not 1. So if you look at the probability of this guy, you are just absolutely away from probability 1, which is the amplitude. So you get almost one guarantee of the outcome.
Also, almost one, but not exactly one.
Not exactly one.
Then-
if it's exactly one, it becomes deterministic.
Yeah, then
Yeah.
if you have many ancillary to measure or post-select, then it's still exponentially small when we have many ancillaries to
Oh,
measure.
that's a great question. It's not exponentially small in terms of ancilla. The point is you measure all of the ancilla and all of them return to you 0. That probability is what we
Oh, I see,
are
I see.
considering.
Thank
And
you.
in the end, it's not every single ancilla. It's everything gets to 0. That's a good question. All right. I think I better hurry up a little bit because I do want to show you this cool thing about how to use QSVT to do optimal scaling Hamiltonian simulation. So what is QSVT? So first of all, this is the SVT, singular value decomposition. You may wonder, oh, I have a general matrix A. How do I figure out? Does it mean I have to figure out what they are in order to implement the QSVT circuit? No, you don't need to know that. As long as you know formally there exists something, and QSVT is essentially a circuit black box. You just shove it in, and it will give you a polynomial of it. And you don't need to know exactly what are these singular values, every single component. That's the amazing part. So I'm going to define the general matrix function, which changed the middle part. You may wonder, isn't this the same as the matrix function itself? Just a simple example to say it's not the same. For example, if my function is x squared, you multiply things out, you will see that, okay, unless this v w is identity, otherwise they are not the same. So in general, they are not the same. That's why it's QSVT. It's not polynomial eigenvalues. It's SVT. It's basically SVT and transforming only the middle part. Now, what is the QSVT theorem? There are many different versions of QSVT theorem. I'm only discussing the most simplest one, and we are going to use this as a black box to do Hamiltonian simulation. So the point is, if you have an odd polynomial with all the degree, there is another theorem if you have even polynomial with even degree. Why odd and even together give you almost everything is because you can Taylor span everything. You can grab the odd terms, grab the even terms, and they give you what you want, right? I'm focusing on odd and odd. This is saying that suppose you start with a block encoding of A. On top of that, suppose the polynomial function you want to implement is bounded by 1 from -1 to +1. This is a condition one needs to satisfy. As long as this is true, there is a circuit to give you with only one additional ancilla qubits and implement the generalized matrix function of this polynomial. This is what it is. QSVT is safe. And the cause of it is the degree of this polynomial. You may wonder, how does the circuit, no, the actual derivation takes a lot of mathematical, let's say, obstacles and so on and so forth. I'm not going to show all of that, but just to say this is how the circuit looks like. You will hardmark, and this is the ancilla, additional ancilla you are using. You hardmark, you control rotate, you apply UA, control rotate, apply UA dagger, control rotate UA, and so on and so forth until the very end. This is how the circuit looks like. Just one ancilla, one additional ancilla. Okay. And there is a general version. Say, imagine if you have a Hermitian matrix, in which case the singular value decomposition is the same as eigenvalue decomposition. Then you have a one block encoding with one additional ancillas for all the polynomial, a one block encoding with one additional ancillas for even polynomial, and you sum them together, you will get a 2 subnormalization block encoding because 1 + 1 is 2, with m plus 2 ancilla qubits, because you are using an LCU in terms of 2 terms, you need one additional ancilla, and together this is a theorem of Schrödinger. It's just some nice thing to say, but this is just saying that combining with LCU, you can implement essentially any polynomials, even okay, odd is also okay. Are we okay so far? Please. First. Go ahead.
Here you go.
Is there a trade-off where, because you have less cells, are you adding more deeper circuits or not necessarily?
Yeah, that's a great question. But actually, QSVT is not deeper compared to Taylor. Yeah. So but why LCU is still good is because sometimes you want to do linear combination, not of the same thing, but of different matrices. For that, we will have to use LCU. Otherwise, QSVT is really cool. Question? Okay, cool.
I just want to clarify, so you're saying that when you use QSVT, you basically get compression for SLR for free?
Yeah, almost. Yeah, that's right. That's right.
Okay, but is it like at the cost of like integrating some expensive like 2 gauge or like?
Actually, no, but there is indeed something that I'm not discussing. There is a bunch of control rotations with certain angles. All of these control rotations should be pre-computed on a classical computer using a classical algorithm, and there is libraries for them. You need some classical persons to compute them, but once they are computed, you just use them. Yeah, this is a trade-off. You do some of the work priority on a classical computer, and then you input it here. Yes.
Is there analysis on the scaling of those?
Yeah, there are. Yeah.
Are they doable?
Yeah, they're doable. They're classically, originally it was believed when the system size become larger, it's classically intractable. But people define a number of actually computer scientists and applied mathematicians find really clever ways you can get away with thousands of qubits, not a problem. Thousands of system size, not a problem. Yeah, very efficiently, classically. There's already libraries for it. Okay, so my time is a little bit tight, but just to show you how to do the optimal back to Hamiltonian simulation. QSVT is very general. You can do it for all the things that I discussed, but just to show you one example, Hamiltonian simulation. Okay, so first of all, I'm going to assume alpha equal to 1. Again, if alpha is not equal to 1, take h divided by alpha. That is upper bounded by 1 as your new thing. And you rescale your time from t to alpha t. You treat that as the new time. So alpha equal to 1 is sufficient for my discussion. I'm going to focus on alpha equal to 1. Second thing is that you notice this is just an exponential function. QSVT says as long as I can make it efficiently into polynomial, I'm done. I look at the degree of the polynomial, which gave me the error, and I can, from the error, I know what is the degree, which is the cost, which is like what we did in the first lecture, and I know the cost of it. Well, I have cosine and sine. There are various different ways to write the polynomial expansion. Turns out there is this Jacobi angle expansion, which is the optimal expansion for cosine and sine. That's going to be what I'm going to use it. The precise expression is not important. The point is that once you truncate it, it's going to give you some error. And these are going to be some even polynomial for cosine. The sine is going to be giving you some odd polynomials, which are both can be implemented by QSVT, the odd ones, the even ones. And the number of truncation errors, there is a truncation error that you can write. If you want to get absolute precision, this is the truncation estimate that you need. R is how many, what is the truncation here? There is infinite series, you truncate it into R terms. Are we okay so far? So and then what we will get is that using this order of cost, I have one block encoding of cosine with one additional theta qubits. I have one block encoding of sine with one additional qubits. The only thing that is left over is I want the exponential, which is linear combination of sine and cosine. How do you do that? You have one block encoding, you want to have another block encoding, you want to sum the LCU. But you do QSVT for cosine, QSVT for sine. You sum them in LCU, you get two subnormalization block encoding with two additional theta qubits, because originally you have one with QSVT, and due to the LCU, you get another one. So there are two ancillary qubits. This is it. This is the optimal scaling. Why is it optimal? First of all, it's linear in terms of t. It's even better than Taylor. Taylor is already almost linear in t, but instead of multiplying the two factors, now you have the additive of the two, which is even better. Please. Oh.
Yeah, sorry, just want to clarify, maybe I missed something. So in that polynomial expansion, I'm guessing that when you substitute x into a matrix H, then those t polynomials are really like a matrix polynomial. But maybe I misunderstood, but didn't we also mention that QSVT, that when you implement like some polynomial, it's not really the matrix polynomial, it's this SVT version of
Wonderful question. Wonderful question. It's going to be SVT. How come cosine of, say, H that is actually implementing an eigenvalue transformation? It's because H is a Hermitian matrix. It can be diagonalized by unitaries in an eigenvalue transformation. And the eigenvalue transformation is the same as singular value transformation. Wonderful question. So situation of, that's why I talk about even polynomial versus odd polynomial. Because if that's not the case, if singular value is not the same as eigenvalue, then even an odd polynomial actually implement a different generalized matrix function, and you can no longer sum them up together. This is the thing, which I didn't mention in detail, but if you're interested, come to me, I will explain more to you. This is a perfect question. Any other question? Oh, please.
Any reason why the star
Wonderful question. It's because you have to ask what the circuit is doing for us. It turns out this circuit is doing a singular value transformation for us. That's what the circuit is doing. The previous control the rotation, UA control rotation, U dagger, this circuit, which is the QSVT circuit. What it's doing is it's actually, originally it was first considered for Hermitian matrices. Then it turns out eigenvalue is the same as singular value. That is in literature, quantum signal processing, QST. So people originally was thinking, oh, it's doing a singular eigenvalue transformation. However, later when people start to study non-Hermitian matrices, they realize, oh, it's actually not singular value. It's it's actually not eigenvalue, it's singular value. If you can design a circuit, a different circuit of the similar form, but implement eigenvalue always for non-Hermitian matrix, that will be absolutely amazing. Yeah, good question. Okay, so this is the cost, and it matches theoretical lower bound. Now you have seen the optimal Hamiltonian simulation. This is already very state-of-the-art results for things. Okay. This I already verbally said. You have block encoding of cosine, block encoding of sine. You make a LCU, you make a 2 block encoding factor in the end. But you want a 1 block encoding factor in the denominator, right? This is the only missing part. Together also with Taylor series, I said I can get away with 2 block encoding, but I really want a 1 block encoding. Right? How do we do that? This is the last part. I want to turn the denominator from 2 to 1 in a block encoding fashion. Now it turns out you can do another QSVT. This is the following function, 3x minus 4x cubed. By the way, whenever we do a QSVT, we ask ourselves whether it's a polynomial. Plus, we need to check whether from negative to 1, and this function is bounded by 1. Right? Previously, we are implementing cosine sine, it's always bounded by 1. You can easily check this function from negative 1 to 1 is actually also bounded by 1. So you can indeed use QSVT. Why does this give you what we want? Now that you dive a little bit with this illustration, I have a unit. I have a QSVT, SVT, but what are the singular values of unitary? Singular values, by the way, are defined as root of eigenvalues of U dagger U, which is identity. So they're all 1. So this singular value matrix for unitary matrix is actually identity. So that means that if I can map this function, as long as the input is 1/2, the outcome is 1. You can quickly check the algebra. That's indeed the case. T of 1/2 is equal to 1. I change all of these diagonal ones into diagonal, diagonal 1/2 into diagonal 1, and I'm done. That's precisely what I want. Right? You don't need to know what is B, what is W. It does not matter. You just do this black box. It's done for. It magically the singular values are changed. Why am I doing this with time? So this is saying T 1/2 is equal to 1, and this is indeed a function bounded by 1, from -1 to +1. So when you do the generalized matrix function, we have V, and this is identity. Originally, it's identity divided by 2, so 1/2, 1/2, and 1/2. Because when all the 1/2 now become 1, so you get identity, which is what you want. This is that. Are we okay? But it turns out more remarkably, this technique is in the literature called OAA, obvious amplitude amplification, in the sense that it's amplifying in terms of some success probability, but it's not using any information of the state that you are studying. You look at it, you don't have like amplitude amplification, you do not do reflection around the state that you start with, right? That's pretty cool. And this was discovered before QSVT. So you can do it in QSVT, no problem, with one additional ancilla qubits. However, these folks figure out you can get away with the following circuit. Well, by the way, if you do QSVT, since this is a polynomial of degree 3, so you expect to repeat the circuit 3 times to get what you want. However, all was discovered before QSVT. What they figured is that you can get away with no ancilla qubits and write precisely in this form, and that gave you exactly as what I just discussed with you. It gave you precisely, well, this will take some time to verify. If you're interested, it can be an exercise, or you come to me, I can write it all together with you. The thing is that 1, 2, 3, you do it 3 times, and it turns out this gave you exactly, this is 3x minus 4x cubed. They give you exactly that. But there is a very important condition for it, which is stating A is close to a unitary, so that A dagger A is 1. In all these, together with the singular value, which is all the 1/2 mapping to 1. If A is not unitary, the singular values are all different values. You cannot just get away with mapping one value to 1 correctly. You need to somehow map all of these values somehow in a uniform rate so that you are not changing what matrix you are representing. But what's the success probability? That's another advanced research topic that if you're interested, you can come talk to me. I can show you how to do that. Okay, so now is the summary. We have throughout these 2 lectures, we have talked about Hamiltonian simulation and expected cost, 2 sort of cool numerical analysis techniques, one for global, one for local. And then we talk about block encoding. Specifically, we look at linear combination of unitaries, how to do that, and how to get away with only 1 ancilla qubits for polynomials using QSVT. And the algorithms when applied to Hamiltonian simulation, we have the chauderization, we have the Taylor series, we have also the QSVT in terms of the rigorous error analysis. And the cost estimate is like this. Is just to summarize what we have already proved. Okay, this is a piece order, and this is the truncated Taylor, and this is the QSVT. All right, and QSVT is the best. It's easy to implement. Well, it needs ancillas versus Chauder do not. So it's your preference. And maybe some exercise would be so the truncated Taylor series technique. The whole discussion. Transfer almost effortlessly to time-dependent Hamiltonian for Dyson series. The whole thing just works out. You can play around with it. I guarantee you, all the analysis you are already ready to do it. And then what about dynamics that are not unitary. I said that unitary, all the identities, if they are not unitary, it's difficult. But you may wonder, I just specify a constant. A constant multiplication is a polynomial. What's the big deal? The issue is that you also need to make sure the function from -1 to +1 is bounded. You cannot just multiply any scalar function. It's not going to be bounded. You agree with me? You multiply by 10, it's not going to be bounded. And that's not a polynomial you can use. So that's, but generally there exists some uniform singular amplification techniques where can be discussed there. And also, this discussion of, well, QSVT can be also applied to design a version of HHL. I think this QSVT version, if you are familiar with these black box theorems, are easier to work out. It will take, say, 15 more minutes, which I'm not able to do here. But if you are interested, please come to talk to me. So you are ready to do all of these. So with that, I want to thank you for your attention. These are some nice references, especially this QSVT one. The archive version is a very good reference.
Okay. Ready?
Thank you. Question about the oblivious amplitude amplification. Like, if I understood correctly, you meant to get rid of this two factor that comes from the summation of cosine and sine, right? Could something like this be done in case every single block, like to get rid of the alphas, let's say, of the single block encodings, or is it too much?
Yeah, that's a great question. So for any general alpha, as long as it's unitary, so even if your subnormalization factor is not 2, it's any arbitrary alpha. But if your dynamics is unitary, all these, you have the unitary divided by alpha, all the diagonal, the singular values are all the same. So the task would be, you want to come up with a function that is from -1 to +1 bounded. Hopefully you have even degree polynomial, and it maps 1/alpha to 1.
Okay.
That function can definitely be defined, and the degree is also 3.
Okay.
Yeah,
okay.
that's
Thank
a great question. So
And
that's the actual goal. The very nice ONA only works out when the alpha is precisely 2. But for general alpha, you can use QSVT, not a.
okay.
Yeah.
Okay. Thank you. And another question, like, so the complexity that we saw, basically, it was all about truncation error, let's say, and we're not really considering, like, for example, I don't know if we write H, like we have an Hamiltonian, we write it as a linear combination of unitary. Like, I guess this can also scale exponentially, right? So we're not considering the complexity right now of the single block encoding, right?
Yeah, that is right. But the thing is that if you have a Hamiltonian that you write out in a linear combination of unitary with a error, and this whole thing can be carried out in the same as the variation of constant, the techniques that I show as the linear error. You have this thing, which you have a Hamiltonian is H. You have a Hamiltonian is H plus R, and you can look at the error as a differential equation, and you can integrate it to get how the error grow in terms of time. So R will grow in terms of time. So this will tell you coming back how many terms in the truncations. But for us, we are in this talk, I'm dealing with the case. We are already given a Hamiltonian, say a transverse IC model, where all the terms are already given.
Okay.
Yeah. Okay. Otherwise, this you can also work out the analysis.
Okay. But yeah. Okay. No, because I was just thinking, like, in the case in which this linear combination of unitaries like scales exponentially, if we just look at the block encoding, like at least the select part, like we still have an exponential number of terms there, right? Because we have all these controlled unitaries that, so it could also.
You mean exponential number of terms or exponential number of? So I think so K, we have K number of terms. Add up in this truncated Taylor series, for example.
No, I mean for single block encoding.
Oh, for single block encoding.
Yeah. But we can also maybe discuss it later.
You mean for single block encoding?
Yes.
What's the question?
Okay. So the idea is using LCU for implementing block encoding. So we have Hamiltonian. We write it down as a combination of unitaries.
Yeah.
And then we use that to block encode.
Yeah, exactly. Say, great point. So if I have transverse field item model, I have a k-local Hamiltonian. How do you do that? Well, you first use LCU to write the block encoding of your Hamiltonian. You have a block encoding, and then you do QSVT, or you do your favorite base. And yeah, so LCU is powerful. Not just is beyond the polynomials, is you can also use it as an input model. Yeah, just
Okay.
as what is.
Yeah. Thank you very much.